The lesson today is on the definition of derivative. A derivative is defined in calculus as the limit as h approaches 0 of f of x plus h minus f of x all over h. The notation is f prime of x, and this is provided that the limit exists. Derivative is represented by the slope of a tangent line, so the derivative of a curve at a point is the slope of the tangent line there. The average rate of change is represented geometrically by the slope of a secant line. It describes how fast and in what capacity a function is changing at any instant. This is a picture of what it looks like to have the slope of change in y divided by the change in x. This would be a typical definition using a secant line with 2 points. What we're going to focus on is narrowing down that gap and using h as a point that's very, very close to point A on a graph. If a function has a derivative, it is considered to be differentiable. We say that f prime exists and that f has a derivative or is differentiable at x. A function differentiable at every point in its domain is a differentiable function. Please remember that it says in its domain. Here's an example, x squared. We've already looked at x squared and figured out what the slope is at a point. This will also tell us for the derivative at many different points. By using the definition of derivative, we can then figure out, no matter what the value of x is, what the slope is at many points. Our example here, our derivative, as you can see, is 2x. If I want to know the slope at x equals 4, we would plug in 4 for x. So the slope would be 8. If I want to know at x equals negative 5, for example, I would plug in negative 5. The slope would be negative 10. Another alternate definition of derivative is limit as x approaches a of f of x minus f of a over x minus a, where the limit exists. These are all different notations for derivative. Y prime dy dx, which is the derivative of with y with respect to x, df dx, and ddx of f at x, or the derivative of f at x. Here's the graph of the derivative from the function and how it works. As we can see here, if we draw the tangent lines and look at the slopes, we can have a general idea of how the slopes of each of the different pieces of the lines work. We can also look at the steepness of the slopes of the tangent lines described by the data. As we look at the graph, we can tell that when I have a positive slope on the slope graph, we are above the x-axis. That would be this part here. When we have a slope of 0 on the graph of the function, we are on the x-axis. When we have a negative slope, we're below the x-axis. Again, here we're on the x-axis, and then when there's a positive slope, again we're above the x-axis. Where the slope is 0 is where the function derivative and the actual graph will have the same x-coordinates. So look at the coordinates to check. Where is the graph going to have a slope of 0? Where there's a positive slope, the steeper the slope, the higher up on the graph you'll be on the derivative graph. The less steep slope will then be lower on the graph of the derivative graph towards the x-axis because it has a smaller slope. Same thing on the negative slopes. And as you go across the graph then, using the tangent lines, we can describe if the graph is positive above the x-axis, 0 on the x-axis, or negative below the x-axis. We can also take a look at what the graph of a function looks like by estimating the slopes at various points and coming up with values. Oftentimes we don't need to know the exact value of the slope, we just need to be able to recognize the derivative graph and the function graphs from each other. When we have one-sided derivatives, we look at each of the derivatives at a specific point and what's called the right-hand and the left-hand derivative to see if the left and right-hand derivative exist. The right and left-hand derivatives may be defined at any point of a function's domain. The usual relationship between one and two-sided limits holds for derivatives and allows us to conclude a function has two-sided derivatives at a point if and only if the function's right-hand and left-hand derivatives are defined and equal at that point. Here's an example of what it looks like to have a limit as h approaches 0 from the right versus the limit as h approaches 0 from the left. Here's an example. Our one function is x squared. We're finding the derivative at 0 for each piece of it in the piecewise function. The slope is 0. When we plug in the other point and find the derivative, the slope is 2. We know that the derivative of x squared, which we've already found, has a derivative of 2x. So slope, when we plug in 0, the derivative at 0 is equal to 0. On the other one, we know that the derivative of any straight line is the slope of that line because the slope doesn't change on a straight line. In this case, the slope is 2. So the left-hand derivative equals 0 and the right-hand derivative equals 2. The derivatives are not equal at 0, so it does not have a derivative at 0. Here's another example. This is how we defined our absolute value function in calculus. Negative x and positive x. Again, we know that the slope of negative x is always negative 1. The slope of positive x is always a positive 1. So the limit from the right does not equal the limit from the left. Therefore, it does not have a derivative at 0. That's our lesson for today.